Hello and welcome everyone to our weekly session. It's the latest in Bitcoin tech where we go through the Bitcoin Optech newsletter. And this week we will go through the newsletter number 327 published on 1st of November 2024. As every week we have two news articles and one release and a few notable code and documentation changes. Let's see how much of it will we be able to cover. Commencing with the preface of the newsletter. This week's newsletter describes a proposal for a timeout tree channel factories and summarizes a draft bid for proofs of discrete log equivalence to be used when generating silent payments. Also included are our regular sections with announcements of new software releases and descriptions of notable changes made to popular Bitcoin infrastructure. So the first news article is titled Timeout Tree Channel Factories. This is a very detailed article. Basically, this is a summary of, I believe, months and months of research, and it is an amalgamation of lots and lots of topics from Duplex micropayment channels. What are they? What are Spillman-style micropayment channels? Then what are covenants? What are channel factories? What's the lightning channel? And what are LN penalties? Like a lot of different concepts have been combined together in this proposal. And this is more or less a research-oriented article, but we'll try and cover as much of it as we can. And those who are interested can then further dig into this and access the resources that have been highlighted in this news article. I'll try and break it into pieces, all right, so that we don't lose track of it. We'll take paragraphs and then focus on those paragraphs and then move on to the next one. So timeout tree channel factories. This is pronounced as Z-Man. It's a pseudonym, all right, of a developer. This is pronounced as Z-Man. So Z-Man posted to Delving Bitcoin and discussed with Optech contributors a proposal for a new multi-layer channel factory design named Superscaler. A goal of the design is to provide a construction that could be easily implemented by a single vendor without waiting for large protocol changes that require widespread agreement. For example, a Lightning service provider, LSP, that distributes wallet software could allow its users to more cheaply open channels and receive inbound liquidity without sacrificing LN's trustlessness. So we all know what the Lightning network is and what problem it is trying to solve. So a Bitcoin as a settlement layer for micropayments is not very conducive and doesn't scale very well because of the confirmation time and the fees. And that is why layer 2 protocols are used for making micropayments. And the most relevant and the most popular among all of them is the Lightning network that we use to make micropayments. All right. Now, Lightning network comes with its own sets of restrictions as well. Okay, there is only a limit to which a Lightning network can scale currently without any hassles. All right. Now, this proposal is what it does is it proposes or it suggests avenues to incorporate in the Lightning network that makes Lightning network more conducive for micropayments and enhances adoption. Because like to use Lightning payments, you need to in transaction and a commitment transaction. So again, you need to possess UTXO, right? Even if you want to buy a cup of coffee with the Lightning network, you need to have a UTXO in possession on the mainnet, right? And then you need to use that as a funding transaction. And once you've done making the payments on the Lightning network, then you use your commitment transaction. Okay. Now, as a vendor, for instance, if you want to incentivize your users or your customers to use the Lightning network, you should come up with means that make accessing the Lightning network easy for your customers. If you, for instance, if you run a restaurant and you want people to make Lightning payments every single time somebody comes to your restaurant and they want to make a payment over the Lightning network, they need to have a funding transaction and a commitment transaction. All of this is pretty cumbersome. So you need to make onboarding to the Lightning network very easy for it to scale. So this is a problem that this specific proposal tackles, all right? And that's why it's named Superscaler. We know that up till now, to open a Lightning channel, you need two people, right? We have a Lightning channel that can have two parties. First, we need to understand what a channel factory is, okay? So basically, a channel factory is, what it does is it facilitates multiple Lightning channels with one on-chain transaction. Okay, so up till now, what happens is that if two people want to set up a Lightning channel, they need to have one on-chain transaction at least for starting that channel. And uh, if you want to establish two channels, then you need two funding transactions, three channels, three funding transactions, four channels, four funding transactions, right? So it scales in a linear manner. What channel factories do is that they allow you to set up multiple Lightning channels with less number of funding transactions than the contemporary way of LN channels. All right. How does that happen? Channel factories are a multi-user contract capable of opening payment channels without putting the channel open transaction on chain. For example, three users create a channel factory by each of them depositing some funds to an on-chain 3 of 3 multisig address. Using non-broadcast off-chain spends from that address, they open payment channels with each other, Alice with Bob, Alice with Charlie, and Bob with Charlie. They can then use those channels with the same security as if they had opened them on chain, because if necessary, they can broadcast the channel open transactions. However, they don't need to broadcast those transactions if both parties act cooperatively, allowing them to reduce the amount of blockchain data used. For large numbers of users under ideal situations, channel factories can reduce the on-chain size and fee cost of LN by 90% or more. Okay, so usually if Alice and Bob want to open a channel with each other, and Alice and Charlie want to open a channel with each other, and Bob and Charlie want to open a channel with each other, Alice and Bob will leave one funding transaction on chain. Alice and Charlie will need another funding transaction on chain. Bob and Charlie will need another funding transaction on chain. So we will need three separate funding transactions on the chain. What channel factories do is that Alice, Bob, and Charlie can come together and deposit their funds in a 3 of 3 multi-sig address. Okay, so all of them come and deposit their transactions in a 3 of 3 multi-sig address, and they can use that 3 of 3 multi-sig address to fund their Lightning channel. This Lightning channel, this Lightning channel, this channel, Lightning channel, and that funding transaction need not go on chain. It'll be off chain. Okay, that specific funding transaction which is spending from this 3 of 3 multi-sig address, you don't need to send that off chain. You just need to create it. You don't need to broadcast it. And every single time you update the status of the Lightning channel, you keep on updating that funding transaction. And only when you want to close the channel do you go off chain. So what this does is, instead of using a unique funding transaction for Alice and Bob, another one for Alice and Charlie, and another one for Bob and Charlie, just create one funding transaction, okay, which is spent to this 3 of 3 multisig address, okay, and then you use that as a funding transaction to fund these three Lightning channels. All right, so this reduces the on-chain burden. This is what channel factories achieve. All right. So one such proposal of the channel factories is named as superscalar. Okay. So what is the use case? For example, a Lightning service provider LSP that distributes wallet software could allow its users to more cheaply open channels and receive inbound liquidity without sacrificing LN's trustlessness. Right. So instead of having a unique funding transaction every single time, a customer of an LSP or a user of an LSP service provider wants to avail the services, instead of creating a new funding transaction every single time, they can create one large funding transaction and use that funding transaction to create Lightning channels, and the funding transaction of those Lightning channels will be off chain. They will not be broadcasted. Okay, that is what channel factories do. And let me see, there is a very nice explanation to it on Bitcoin Stack Exchange channel factories. Bitcoin Stack Exchange. Okay, so later on, you all can refer to this as well. What are channel factories and how do they work? Yes. Okay. So, if you have three users, all right, you can open three channels. If you have four users, you can open six channels. Okay. So if you don't use channel factories, if you use the conventional way of opening Lightning channels, then with four users, you will need four funding transactions. Okay, so four users can start only four channels. But if all those four users come and park their funds in a 4 of 4 multi-sig transaction, then with that 4 of 4 multi-sig transaction, a multi-sig account, they can open six channels. Okay, so with three three users, you can open three channels. With four users, so here there's no upgrade basically, except size that you save. But with 4 users, you can open 6 channels. With 5 users, you can open 10 channels. With the conventional mechanism, if you want 10 channels, you will need to have 10 funding transactions. But with channel factories, if 5 users come and they park their funds in a 505 multi-sig account, they can open 10 channels. So you don't need 10 funding transactions, you only need 5 funding transactions. All right. So that is how you optimize with 615, with 721, with 828. All right. So you can read this answer. It's a very beneficial and a very elaborate answer. Okay. So this is how channel factories work. The overall construction is based on a timeout tree where a funding transaction pays to a tree of predefined child transactions that ultimately spend off-chain into many separate payment channels. After a configurable timeout, example a month, some of the parties involved in the timeout tree forfeit any of their funds remaining in the tree. This incentivizes them to withdraw or find alternative security for those funds before the expiry, which can encourage the use of cheap off-chain mechanisms rather than publishing parts of the tree on-chain. In previously described, okay, we'll come to this later, okay. So what is this one thing peculiar about this is firstly, it's a timeout tree, okay. So basically what happens is that you use the funding transaction of the channel factory that we just discussed, okay. In our example, we discussed a 3 of 3. Okay, 3 of 3, it could be a 10 of 10, it could be a 50 of 50, it could be a 100 of 100. So 100 people who want to use the Lightning Network come together and park their funds in a 100 of 100 multi-sig transaction. And then they use that transaction to create funding transactions for their Lightning channels, which they create but they do not broadcast. Which they create and they do not broadcast. Okay, now that is why we call it a tree. Okay, we call it a tree because if there are 100 people that want to open lightning channels with them, then we create a tree of those lightning channels. We create a tree of those lightning channels. That is where the name timeout tree comes from. And the leaves in those trees represents lightning channels, and they are arranged in a hierarchical manner, depending upon the amount of liquidity that they would need and depending upon the kind of user that it is. So users that frequently use are clubbed together on the same hierarchical level. Users that require high inbound liquidity are clubbed together at the same hierarchical level. So that is how the tree is arranged. Anybody who wants to go into detail can have a look at it later on, because that I believe will be outside the purview of this session. It's a very, very, very long article, I believe, worth months of research. So this is where this entire concept is explained. And I can keep scrolling and scrolling and scrolling and scrolling and scrolling and scrolling. It'll probably take a couple of days at least for somebody who's interested to try and understand this in detail. But the point being, what we've covered thus far is what are channel factories? Channel factories are basically avenues that allow you to create multiple lightning channels without broadcasting their specific funding transaction to the mainnet. So the number of people that are interested in transacting with each other on the Lightning Network come together and they park their funds in a multi-sig account, and then they use that multi-sig account to fund to create funding transactions which they don't broadcast on the mainnet, and those funding transactions are arranged in the form of a tree, and that is where this term tree comes from. And the leaves of the tree are arranged in hierarchical order on the basis of the amount of liquidity that a specific funding channel, lightning channel would require, or on the basis of the amount of activity that a lightning channel provides. Why do we call it a timeout tree? Because it has a timeout. It has a timeout. After a configurable timeout, example, a month, some of the parties involved in the timeout tree forfeit any of their funds remaining in the tree. This incentivizes them to withdraw or find alternative security for those funds before the expiry, which can encourage the use of cheap on-chain mechanisms rather than publishing parts of the tree on-chain. Okay, so after 1 month, these trees or these channels are configurable to an amount of time. Like you can set an expiry date for those channels. Okay, and after that expiry date has been set, what happens is that either you settle the transaction on the mainnet, or you use the fund, or you transfer the fund to some other lightning channel. Either you settle the funds on the mainnet or you transfer them to some other lightning channel. Okay, and after 1 month, if you don't do that, then what happens? In previously described timeout trees, user funds that timed out became the property of a service provider, But Zeman reverses this and makes the service providers find out funds become the property of the users. This places the burden of getting transactions confirmed on the service provider rather than the end users. So if before a month or whatever is the expiry date of that lightning channel, okay, or if the funds are not settled in the main on the main net, okay, then the funds of the service provider, the LSP provider go to the will go to the user. Will go to the user. So the onus of settling the transaction is upon the LSP provider. All right. What this does is that it increases adoption. For instance, there is like I gave an example of a restaurant owner. Okay, there's a restaurant owner who wants to onboard people to the Lightning Network, who wants their customers to use the Lightning Network. Now, one big barrier that comes is that the customers, like I just said, need to have on-chain UTXOs. So to open your own Lightning channel, you need to have access to on-chain UTXOs. You need to create a funding transaction. Then you need to create a commitment transaction, which might deter a lot of people from using the Lightning Network. In this situation, what happens is that the user or the customer does not have to create a funding transaction on chain, right? They do not have to create a specific funding transaction on chain. They already have a channel factory using which they can create a funding transaction for the Lightning channel, which they do not broadcast on chain, and they can set an expiry period for this Lightning channel. Before it expires, the onus is upon the LSP provider. In our example, the restaurant owner, to either transfer those funds to another Lightning channel or to settle them on the mainnet. All right. So the onus of going on chain is not upon the user; it's upon the LSP service provider, which can enhance the percentage of the people using the Lightning Network, like the commoners using Lightning Network. Because as a user, as an end user, it would deter you to set up a funding transaction and pay fee for that, then set up a commitment transaction and pay fee for that. In this situation, what's happening is that you already have a Lightning channel established and funded by your channel factory, and you don't have to pay anything to go off chain. It is upon the LSP service provider to take the transaction on chain before the expiry date. Okay. So this is broadly what this proposal aims to achieve. We'll go through it further. Timeout trees use Timeout trees used require each involved party to contribute a signature. This avoids the need for consensus changes but limits the practical maximum number of users in a factory due to the well-known multi-signer coordination problem. Okay, so this proposal was also proposed easy earlier. Okay, but it was slightly difficult. It was proposed in the form of a covenant. Okay, I think it's in newsletter 270. It was proposed in the form of a covenant, which requires a soft fork. This proposal does not require a soft fork. This proposal does not require a soft fork. Okay, but because it does not require a soft fork, it induces what is known as a multi-signer coordination problem. What does it mean? It means that all the number of people that are participating in a channel factory need to be present to sign the multi-sig account, right? Even if one of them is not present, then all your efforts go in vain. How does that happen? Okay, we just read through this. John Law posted to the Bitcoin Dev and Lightning Dev mailing list the summary of a paper he's written about creating very large channel factories using covenants and managing the resultant channels using adaptations of several previous protocols he's described. He begins by describing a scalability problem with signature-based protocols that require participation from a large number of users, such as coin joins or previous factory designs. If 1,000 users agree to participate in the protocol, but one of them becomes unavailable during signing, the other 999 signatures are useless. If during the next attempt another individual user becomes unavailable, the other 998 signatures collected in the second attempt are useless. All right, I hope you're getting what I'm trying to say. Okay, so here, like we saw, if there are three users, all three of them need to be present, right? Because if there are three users in a three of three multi-sig account, all three need to sign it, right? If two people sign it and one doesn't, then those two signatures are of no use. Likewise, if you have 10 people, we need all 10 of them to be available to make signatures. Even if one of them abandons or is not available, the other nine signatures are not useful. Okay, so if in a channel factory there are 100 users, okay, if in a channel factory there are 100 users and all 100 of them come and park their funds in a 100 multi-sig account, all 100 of them should be available at the same time, or all 1,000 of them should be available at the same time to make signatures. Okay, even if one of them abandons or is unavailable for some reason, even if 999 people sign, those signatures are useless and are absolutely of no avail. Okay. Now let's say you dump that one person, and then you start with 999 people. You create a new script with 999 people. Now again, if one person abandons and 998 people sign, again it's of no use. Okay, so this is what is known as multi-signer coordination problem. In a n of n multi-sig account, you need all of those n signers or signatories to be available. In channel factories, with this proposal that we are considering or we are discussing, if you wanted to scale to hundreds and thousands of people, you need to ensure that all of those people need to be present to sign at the same time. Even if one of them abandons or is not reachable, the entire protocol fails flat on its head. All right. And that is why an alternative was suggested in newsletter 270 using covenants. Like whoever is interested can go in and read how it works. Okay. So, but the catch with covenants is that you need a soft fork, and soft forks, as we know, are not very easy in Bitcoin to achieve. All right. So it's like a cash 22 situation, or you can call it opportunity cost. In economics, they call it opportunity cost situation. If you want scalability, then one avenue is a soft fork of OpCTV, and which obviously requires a consensus of the community, which is always not easy to achieve. And if you want to achieve channel factories that scale without covenants, then you need multi-signature accounts, which brings you to the problem of multi-signer coordination problem. Okay, so one way or the other, but the one that we are discussing currently, it does not take into consideration any covenants. It uses the current protocol, okay, but then it induces the multi-signature coordination problem. All right. I'll just revise once again. We are talking about channel factories. What do channel factories do? Okay, what channel factories are multi-user contract capable of opening payment channels without putting the channel open transaction on chain. Okay, so channel factories are basically a mechanism that allow multiple people to come together and pump their funds in an N of N multi-sig account, which they can use to fund lightning channels. And each funding transaction or every funding transaction that pays out of that channel factory need not go on chain. It need not go on chain, and this is how it scales. Okay, so if four people come together, they can create six channels. If five people come together, they can create 10 channels. If six people come together, they can create 15 channels without having to broadcast the funding transactions of those channels on the mainnet. Okay, this is what our channel factories achieve. And these channel factories are paying for timeout trees. Trees because each lightning channel is referred to as a leaf in a tree, and those leaves are arranged in hierarchical order of similitude. So channels that require high liquidity are arranged in one hierarchy, and channels that require low liquidity are arranged in one hierarchy. And they have a timeout, meaning they can expire. Their expiry is configurable, and once they expire, the onus is upon the LSP service provider to either switch those funds to another L2 channel or to settle it on the mainnet. Otherwise, it is the user that claims all the funds. Okay, and this specific protocol that we are discussing about, it does not involve the any covenants. Okay, unlike the one previously discussed in newsletter 270, rather it uses the current and the existing consensus rules, and requires all the participants in the channel factory to be present at the same time to sign the multi-sig transaction. But then again, it induces what? It induces the multi-signer coordination problem, even if one of the people is not available. So one out of these 10 users is not available, the protocol doesn't go through. So if you have 1,000 people and even if 999 of them are there and one person is not available, the protocol does not go through. Most of the leaves of the timeout tree are off-chain funding transactions for the common type of channel used today, LN penalty, allowing some reuse of existing code for managing LN channels. The counterparties in each channel are an end user and the Lightning service provider who created the timeout tree. Some of the leaves of the tree may also be exclusively controlled by the LSP for purpose of rebalancing fund. Okay, so what are the leaves of these three? They are lightning channels. Okay, and these lightning channels incorporate the current LN penalty mechanism. What is the current LNT? I'm sorry, what is the current LN penalty mechanism? It is uh, the revocation transaction, right? So if any person tries to submit a status of the transaction to the mainnet, which is revoked, then all of the funds will be given to the counterparty. We've discussed this in detail, what an LN penalty is. All right, so it uses the same mechanism of punishing the cheater. And who are the counterparties? The one counterparty will always be the Lightning service provider, and other will be the end user. Okay, now some of these leaves, like I just discussed, the leaves will be arranged in hierarchical order of the similitude. Some of the leaves of the tree may also be exclusively controlled by the LSP for the purpose of rebalancing funds. So the LSP provider might reserve some leaves in the timeout tree only for a liquidity balancement. So liquidity balancing. Okay, so if the LSP service provider runs out of liquidity, then they can reserve certain leaves which will only be used to inject liquidity into the timeout tree. Between the root and the leaves are duplex micropayment channels. Unlike any penalty channels, duplex channels allow more than two parties to safely share funds. However, they also only allow a relatively small number of state updates compared to LN penalties, effectively unlimited number of updates. Okay, so between the root and the leaves are duplex micropayment channels. So some of the leaves will contain of the duplex micropayment channels. Okay, what are duplex micropayment channels? Like I said, there are lots and lots of concepts that have been merged in this one proposal. It's an amalgamation of a dozen of concepts, and we're trying our best to go through each one of them. What's a duplex micropayment channel? Duplex micropayment channels are bidirectional micropayment channels, okay? And that use de-incrementing relative time locks to ensure the latest state is the first that can be confirmed compared to bidirectional errant penalty channels, okay? So in conventional lightning channels, what do we have? We have this concept of HTLCs, right? HTLCs have time lock, are time lock. So anybody who tries to broadcast the any specific state of a lightning channel to the main net, okay, the counterparty is given a certain time. The counterparty is given a certain time, and within that time frame, the counterparty determines or catches the person who has broadcasted the final state to the main net. If they catch them cheating and they prove that they are cheating, then they can claim all the funds. So if Alice and Bob are have a lightning channel with each other, and Alice broadcasts the commitment transaction on the mainnet, and Alice has broadcast a revoked commitment transaction on the mainnet. This this commitment transaction that Alice has broadcasted will have a time lock. Within that time lock, if Bob can prove that Alice is cheating and submitting a revoked commitment transaction, then all the funds in the Lightning channel go to Bob. Okay, this is what we refer to as LN penalty channel. Okay, now, duplex micropayment channels work in a different mechanism. What they do is that they de-increment the time lock with every status update. Okay, so if Alice and Bob have a Lightning channel and they update the status, okay, Alice makes some payment to Bob over that Lightning channel. They have a certain time lock for that. Let's say that time lock is for n seconds. Now Alice makes some more payment, and again they update the status. So the next time the time lock is going to be, let's say, n minus 10 seconds. Again, Alice sends some funds to Bob. So the third time they updates the status of the Lightning channel. The third time the time lock, let's say, will be n minus 20, and then the fourth time n minus 30, and then the fifth time n minus 50. So every single time there is a update in the status of the Lightning channel, the time lock is de-incremented. The time lock is de-incremented, meaning that in any situation, the latest state will only be the state that is broadcasted on the mainnet, right? Because the old state had a time lock of n seconds, then the next one had n minus 10, the next one had n minus 20, the next one n minus 30, and then n minus 40, and then n minus 50. If all of them are broadcasted to the mainnet, then it is obvious that the status of the Lightning channel, which had n minus 50 seconds as the time lock, is the one that will get confirmed. Okay, so you don't need to check whether your counterparty is cheating and then punish them and claim that they have furnished a revoked commitment transaction, because every state of the Lightning channel is being updated with a smaller time lock. Even if all of them are broadcasted simultaneously, it is always going to be the final state that gets confirmed on the mainnet uh, before the other states. Okay, so this is what is duplex micropayment channels. So they don't use the penalty mechanism, rather they use the decrementing of the relative time locks to ensure that the latest state is the first that can be confirmed. Unlike LN penalty channels, duplex channels allow more than two parties to safely share funds. However, they also only allow a relatively small number of state updates compared to LN penalties' effectively unlimited number of updates. The intermediate duplex channels are used to allow rebalances involving the LSP and two end users. Okay, so we just talked the fact that certain leaves in the timeout tree will be reserved for the LSP service provider, which will only be used for liquidity management. So they can have two end users. They can establish these channels with two end users, okay, who and those end users, I mean, these channels will be used for liquidity management. These rebalances could securely complete at off-chain speeds, allowing a user to receive an incoming payment almost instantly, even if they didn't previously have enough capacity in the channel to accept it, right? So if there is a lightning channel that runs out of capacity, the LSP service provider can use these specific leaves that they have established with two end users to use that liquidity and transfer it to other lightning channels which have run out of liquidity, to ensure that even if they have a certain channel in which they lack liquidity, they can immediately inject liquidity into that channel. In a later post, Zeman described replacing part of a duplex channel with Spillman-style micropayment channel. This would be more efficient on-chain in the case of a cooperative close, although it would be less efficient on-chain in the case of a unilateral close. Okay, so in a later proposal, this proposal was fine-tuned over a period of time. In a later proposal, the duplex micropayments were replaced by Spillman-style payments. What are Spillman-style payments? All right, we just read it in a brief. Spillman payment channels are unidirectional. There is a payer and a payee, and it is not possible to transfer money back in the reverse direction. So these are unidirectional, right? What are the duplex micropayment channels? They are bidirectional, meaning both the channel parties can transfer funds in each other's directions. But Spillman style payment channels, they're unidirectional, meaning there's only one payer and the other is merely a recipient. Spillman payment channels expire after a specific time. The receiver needs to close the channel before the expiration. The proposal received a moderate amount of discussion. The author said that one of the weaknesses of the proposal is its technical complexity. As we saw, this is not a very straightforward proposal to understand. It's technically complex and an amalgamation of multiple different protocols and concepts. So yeah, the people who observed it commented on the discussion, I believe, on Delving Bitcoin. The author said that one of the weaknesses of the proposal is its technical complexity due to the use of multiple different channel types, plus the inherent channel in any channel factory design of managing additional off-chain state. However, the proposal has the advantage of being something that could be implemented by a single team and made interoperable with the standard LN without requiring many changes to the LN protocol. Coming back to where we started from, the author believes that the USP or the standout thing of this proposal, unlike its predecessor, is that it does not require any soft forks. It does not require soft fork. It uses the resources and the protocols and the tools and the avenues that we have at hand to achieve scalability on the Lightning Network without the incorporation of any soft fork. So this is what we had to cover about what channel factories are, what are the use cases, what are timeout trees, what is the multi-signer coordination problem, what are ailing penalties, what are duplex micropayments, what are Spillman style micropayment channels, and how this proposal aims to scale Lightning Network without relying on any governance. All right, and there is a lot to it. Like I said, if you go to where did that post go? If you go to Delving Bitcoin, probably take a couple of days for you to just try and understand what the entire proposal is. We try to summarize it as much as we can and understand it on a high level, what it's trying to achieve. Anybody who's interested in digging deep into it can do that at their own pace and convenience. If there are any questions, any thoughts, any comments, please feel free to unmute yourself and ask or post in the comment section. Somebody posted something. Hello, Faisal. Hello, Pointy. All right, cool.
Faisal, for channel factories, like you mentioned, if there are 5 Lightning nodes, it can create 10 channel factories, and for 3, it can create maybe 6. That's the number 6, or like how do you the number of n folds?
Yeah. Okay. So I think this will help us better. Okay. So currently we have Alice, Bob, and Charlie, 3 people. If we had Alice, Bob, Charlie, and Dan, okay, and let's assume we are using the conventional way of creating lightning channels between them. So Alice and Bob will need one channel. For that, they will need one funding transaction. Then Alice and Charlie will need one channel for which they will need one funding transaction. Then Alice and Dan will need one channel for which they will need one funding transaction. Okay, so we already have three funding transactions. Then Bob and Charlie, one funding transaction. Bob and Dan, one more funding transaction. That's five, right? And then Charlie and Dan, one funding transaction, six. So for all these four people to establish one unique Lightning channel with each other, they will need six funding transactions. Okay. Alice with Bob, Alice with Charlie, Alice with Dan. Okay, then Bob with Charlie, Bob with Dan, then Charlie with Dan. So we need six funding transactions. But in this case, what all four of these can do is that four of them can come together and create a four multi-sig account, and all four of them, Alice, Bob, Charlie, and Dan, can send one single payment to that 404 multi-sig account. Okay, and then all four of them have their funds parked in that 404 multi-sig account, and then they can use that 404 multi-sig account to create channels with each other. Okay, so they will still have a funding transaction, but they will not broadcast that funding transaction on the mainnet. They will use that channel factory in which all four of them have parked their funds as the source from which they as a source which they will use for settlement, as a source which they will use for settlement. So they will not need an individual funding transaction to go on the main chain. They will just need four funding transactions, four transactions to go on the main chain. Alice paying to the 404 multisig, Bob paying to the 404 multisig, Charlie paying to the 404 multisig, and Dan paying to the 404 multisig. And once they have their funds parked in a 404 multisig account, which is related to a channel factory, then they can use that channel factory to create to create Lightning channels with each other. So instead of six funding transactions going to the mainnet, you just need four funding transactions going to the mainnet. And once you have a channel factory with that 404 multisig account, then they can use it to create individual Lightning channels with each other. And those funding transactions for those six Lightning channels, individual one, they will just create it and not broadcast it on the main.
Okay. Okay.
All right.
I'm still not completely clear on like why do we need such less closing transactions? Like you were saying for closing we just need four, even though there are six channels. For closing we just need to close just four channels, and then we'll close the transaction.
No, we will use six. I mean, if it's conventional, let's forget about channel factories. Okay, if there are four people and all four of them want to open a Lightning channel with each other, a unique Lightning channel with each other, you need six.
Yeah.
That is six opening transactions, six closing transactions, right? But here, what you do is those four people will park their funds in a 404 multisig. So they create a 404 multisig account. Alice pays to it one transaction, Bob pays to it two transactions, Charlie pays to it three transactions, and Dan pays to it four transactions. You will only need four transactions. Then Alice and Bob can open a channel with each other. They can open six channels, right? They can open six channels. And those six channels will have funding transactions. They will create it, but they will not broadcast it. They will not broadcast it. They will just keep updating its state, keep updating its state. And when they want to go off chain, then they will use this 404 multisig account and use that as a parent transaction to create the commitment transaction, not the funding transaction, which is never broadcasted.
Got it. Partially got it. I'll have to revisit Lightning a bit. Okay.
Yeah, sure. And this you can read this answer. I think this will make it more clear. I'll share it because this covers exactly your question. If we had a draw board or something, it would have been ideal, but then it's beyond the purview of our session.
Yeah, I'm just wondering, like the way these teachers teach, they have running PDF, but they also have a draw board. So they on the PDF itself they draw and they erase. If we can use such a tool, it would be like amazing. I'll also Google about it.
Yeah, cool. We can explore that as well. In fact, yeah, I think Probot occasionally does that for the PR review clubs. But even I'll have to explore how we can do that.
Okay.
Cool. All right. So the next one is we've already read 50. We'll try and keep this as short as possible. All right. Draft bid for DLEQ proofs. Andrew Toth posted to the Bitcoin Dev mailing list a draft bit and a link to an implementation for generating and verifying proofs of discrete log equality for the elliptic curve used by Bitcoin, P256K1. A DLEQ EQ allows a party to prove that they know a private key without revealing anything about it, such as its corresponding public key. This has been used in the past to allow someone to prove that they own a UTXO without revealing which UTXO. See news at number 83 and 131. The current BIP is motivated by support for silent payments created using multiple independent signers. If one signer lies or is faulty, it's possible for funds to be lost. A DLEQ allows each signer to prove that they signed correctly without revealing their private keys to the other signers. See newsletter number 308 for previous discussion. The proposal received a reply from Adam Gibson, who previously implemented a DLEQ proof system for the join market CoinJoin implementation. He suggested several changes that would make the BIP's version of DLEQ more flexible for other users beyond silent payments. Okay. So to understand what BIP does, we will first have to understand what silent payments are. Okay, in brief, we'll understand. We'll not go into too much of details, but just understand what silent payments do. Silent payments are a type of payment that can be made to a unique on-chain address for every payment, even though the receiver provided the sender with a reusable off-chain address. This helps improve privacy. Traditionally, a user who receives payments should generate a new Bitcoin address for every payment. This is because receiving multiple payments to the same address reveals that the same user received those payments even if the outputs are later spent in separate transactions. This is known as address reuse. Using a new address often requires a secure interaction between sender and receiver so that the receiver can provide a fresh address every time. However, interaction is often infeasible and in many cases undesirable. With silent payments, a receiver can generate and publish a single silent payment address, eliminating the need for interaction. The sender then selects one or more of their chosen inputs and uses their secret keys together with the public key of the silent payment address to derive a shared secret, which is used to generate the destination. Okay, so initially, what used to happen is that if you want somebody to send a payment to you, a Bitcoin payment to you, you generate an address and you share that address. Now there are two ways of doing that. Either you generate address just once and share it with all the senders, and then they keep using the same address to send payments to you. Okay, now what this does is this compromises privacy because if everybody knows your address and you're giving the same address to multiple people to send payments to you, then they can know exactly how much payment you have, right? So if you generate an address and you give it to 10 people and you tell them to use the same address to send funds to you every time they want to reach out to you, everybody, all of those 10 people know exactly how much Bitcoin you own, which is not an advisable thing to do. Now, the second alternative, or the more privacy conscious alternative, is that you generate a new address every single time you want to receive a payment. Okay? This is what is the ideal situation, but this induces overheads, right? If you have to receive frequent payments every single time, you have to create a Bitcoin address, and then you have to send that Bitcoin address with the person who is going to send payment to you. And this happens obviously off chain, right? There is no avenue for you to share the Bitcoin address on the Bitcoin network. You have to share it off chain. Either it is through an email or through a handwritten note, or your wallet communicates with the wallet of the sender using the internet. Okay, and so basically, it's cumbersome. It induces overhead, especially if you have to frequently receive payments. You have to constantly create a new addresses and send it and send it to the spender. What silent payments does is that it gives you the best of both the worlds. It keeps your privacy intact. At the same time, it reduces the overhead of creating a new address every single time you want to receive a payment. I mean, the overheads of manually creating a new address every single time you want to receive a payment. Okay, it creates a static address. Okay, so you have one static address, or your silent payment address. You can share it with everyone. Every single time they want to make a payment, they will use the static address to generate a new destination address. Okay, they will use the static address, your silent payment address, to create the unique destination address, and they will pay to that destination address. And your silent payment address cannot be linked to your destination address. Okay, so I have a silent payment address which I can give to 10 people. Every single time they want to make a payment to me, they will use that silent payment address to generate a destination address to which they will pay. They will not pay to the silent payment address. They will use the silent payment address to generate a destination address, a unique address, and send it to that address. And anybody who has my silent payment address cannot link cannot find a link between the silent payment address and the destination address. So you cannot look at my silent payment address and then go and look at the blockchain and find a correlation address and figure out that this destination address corresponds to the silent payment address, correct? So it gives you the best of both the worlds. You don't have to create a new address every time you have to receive a payment manually, and at the same time, you get the privacy benefits of having unique addresses, all right? And you circumvent address reuse. So this is what silent payment does. However, there is a catch in it. Okay, so basically, I'm sure we all know about Schnorr signatures. And Schnorr signatures, what they do is that they allow signature aggregation and public key aggregation, right? So multiple people can come together and they can aggregate their public keys and turn it into one public key, or they can aggregate the signatures and turn it into one single signature. Okay. Now in silent payment, what happens is that to create your destination address, you use a shared secret which is created using a private key. You use a private key. Using that private key, you create a shared secret, and then you use that shared secret to create your destination address. Okay, and you also use that same private key to sign the transaction. Okay. Now, the private key that you're using to sign the transaction should also be the same private key that you are using to create that shared secret, right? If you use one private key to sign the transaction and another private key to generate the shared secret, that would be cheating. Okay. Why? Because the shared secret is used to create your shared secret is used to create your output script. Your shared secret is used to create your output script. If you use a private key that does not correspond to the UTXO that you're trying to spend, you will create an erroneous output public key, or the script pub key. Okay. Now, if you use the wrong private key to sign your input, your transaction will be consensus invalid. We all know that, right? If you have an invalid signature, your transaction will be rejected by the nodes. Okay, so if you use the wrong public key to sign the transaction will be considered invalid. So we don't have to check for that. We don't have to check whether the participants in whether the participants who are coming together to create a silent payment, okay, multiple participants who are coming together to create a silent payment, whether they are using the right private key to sign their inputs. We don't have to worry about that. The consensus takes care of that, right? But we have to worry about the fact that they are using the right secret number, the right private key to generate the shared secret, because a transaction with an erroneous script of key is still consensus valid. It is still consensus valid. If you create a wrong silent destination address and the funds that you're spending will go to the wrong address. Okay. So what somebody can do is somebody can create a private key. Let's say there are multiple people who are coming together in a multi-sig transaction or an approved transaction, okay, and they want to create a silent payment address which corresponds to all of them. So 5 people, 10 people come together, they aggregate the signatures, they aggregate the public keys, and they create a silent payment address which all of them will use together. Okay. Now, so what one participant can do is that they will use a private key to sign the input, but they will use a different private key to create the shared secret. Okay. And what that will do is that the transaction will be consensus valid, but the script pub key will be erroneous. The script pub key will be erroneous because the script pub key will use the shared secret that you will create. And if the script pub key is erroneous, your transaction will be consensus valid, but your funds will go to the wrong destination address. So somebody might cheat you, somebody might create a valid signature, but then invalid script pub key, which will lead to an invalid destination address and will destroy or burn all the funds. Okay. Now you need to verify that. How do you verify that? You verify that by something known as a discrete log equality theorem or a protocol, whatever you call it. What does this do? This proves that you have ownership of a UTXO without sharing that exact UTXO. Okay, this is also proposed in some Lightning channel protocols. Okay, that you can open a Lightning channel with funding transaction by proving that you own that funding transaction without having to share which specific transaction it is. This is also known as a zero knowledge proof, where you prove cryptographically that you are the owner of something without exactly sharing what that thing is. Okay, so what you can do is that without without sharing your private key, you can prove that this is the same private key. The private key that you have used to create your shared secret is the same private key that you have used to create your digital signature. Okay, so the private key that you have used to generate the shared secret is the same private key that you have used to create your digital signature. You can verify that using this discrete lock equivalency protocol without having to share your private key. So discrete lock equivalency or proofs of discrete lock equivalency is the ability to prove 2 points on an elliptic curve were both derived from the same private value, such as the private key. Applications of it include committing to ownership of a key in the UTXO set without publicly revealing the specific UTXO and proving a silent payment output was constructed correctly without disclosing the private key. Okay. So in our case, what this does in silent payments, what it does, it proves that we have used the same private key to create our digital signature, which we have used to create the shared secret. Okay. We can use different private keys for creating a digital signature and the shared secret, such that the transaction is consensus valid, but the funds go to an erroneous address. Okay. Now, if anybody is like interested in going into the details of this, I think there's a proposal. Yeah. So all the cryptographic mumbo jumbo is here exactly how that happens. Okay. But if we were to just read what matters the most, uh, so BIP 352, it's a silent payment BIP that requires senders to compute output scripts using ECDH shared secrets. Okay, so it requires this thing known as Diffie-Hellman key exchange. Okay, so if any of you are into cryptography, you know what a Diffie-Hellman key exchange is. It's used in the Lightning Network as well, where two participants create a shared secret. It requires senders to compute output scripts using ECDH share secrets from the same secret keys used to sign the inputs. So you use the same private key to sign the inputs and use the same private key to to create the ECDH shared secrets. Generating an incorrect signature will produce an invalid transaction that will be rejected by consensus, right? So this is not our concern. If somebody using an incorrect private key to sign the transaction, the consensus will take care of it. The nodes will reject it. An incorrectly generated output script can still be consensus valid. So somebody can use an incorrect private key to create the ECDH shared secret with which the output scripts are computed, and it will still be consensus valid. So that is what our catch is. That's it. That is what we want to verify, that the person is using the correct private key to generate the ECDH shared secret, which is used to compute the output scripts. By producing a DLEQ proof for us, the generated ECDH shared secrets, the signing entity can prove to other entities that the output scripts have been generated correctly without revealing the private key. Okay, so the DLEQ proofs can prove to all the participants in multisig a silent payment transaction that every participant has used the same private key that they have used to sign their input, and they've used the same private key to generate the ECDH shared secret with which the output scripts are constructed. So they can be sure that the funds will not get bought and they're going to the correct destination address. Okay, this is how it is achieved. This is like the cryptography of how exactly this proof works, and like you can read this as well. This A is the shared secret, and what all components it needs. All right, so. If A and B are the ECDH public keys and C is their ECDH shared secret computed as C is A into B, the proof establishes that the same secret key A to both A and C without revealing A. All right, so this is the public key, and this is the public key of the destination address, and this is the scalar or the private key. So you can prove that you have used the same scalar to sign the inputs of the UTXO that you have used to create the ECDH shared secret. All right. So yeah, broadly we discuss what silent payments are and how silent payment destination addresses are created and how it's possible for somebody to use a private key in the inputs, but a different private key to generate the ECDH share secrets, thereby creating a consensus valid but an erroneous output script pub key, and how we can validate that using DLEQ proofs to ensure that the same private key or the same scalar value is being used to assign the inputs and create the ECDH shared secrets. All right. Both of these topics that we covered today were like cryptographically very dense. These are like research articles that need months and months of study and research. But I tried my best to summarize them to the best of my ability. It's pretty difficult actually. So if you all got some of it or most of it, that's great. But in any case, you can the resources are here. If any of these topics interest you during your spare time, you can go through the resources and read it in more detail. But that'll require more time. Like in 60 minutes, we did the best we could have. And I hope I was able to at least convey the concepts on a surface level. But yeah, any questions about this news article? Cool. Yeah, someone wants to talk.
No, I'm just saying hats off, Faisal. A lot of new things were there in this newsletter.
Thanks a lot. Okay, BTCpay server. I think most people know it. It's just that a new version has come up. All right. BTCpay server is basically it's an open source software that primarily allows vendors to accept payments, self custodial payments. It gives you access to a Bitcoin node, gives you access to a Lightning node, which you can use to send and receive payments over the Lightning network. And you can see what new features that has added, the new sidebar, improved onboarding flow, improved bundling options, support plug-in and bill rate providers, and I think they also have their own website, BTCpay server. It's pretty popular. It's very popular, in fact. I have never used it, but it's pretty popular. BTCpay server. It's mostly used by merchants and people for accepting donations in a custodial way. So yeah, you can go through their website and familiarize yourself with the features that they provide. You'll generally find this at checkout pages of e-commerce stores, etc., or merchants use it, and people accepting donations basically use it. So yeah, they've come up with the new version of the software. And probably we can just read through this because we have covered this in one of our preceding sessions. In newsletter 310, I think I remember covering this. So Bitcoin Core, PR number 31130 removes universal plug and play UPnP Internet Gateway device IGD support by dropping the mini UPnP dependency, which had a history of security vulnerabilities and was already disabled by default. See newsletter 310. It is now replaced by a port control protocol PCP implementation with a network address translation port mapping protocol, NAT PMP fallback. See newsletter 323, which allows nodes to be reachable without manual configuration, but removes the security risks associated with the mini UPnP dependency. So Bitcoin Core uses a lot of dependencies. All right. So like you must have heard about this sec P256K1. It is a library that is not a part of Bitcoin Core. It is a parallel library that any open source software can use, and Bitcoin Core uses it. This is a very common practice that you don't need to write everything from scratch. Whatever code is available, whatever libraries are already available, you just incorporate them in your project, right? So if somebody has created a cryptographic library, instead of creating your own library, you just incorporate it in your project. So Mini UPnP is a library or a dependency of Bitcoin Core, which was incorporated into Bitcoin. What does it do? So basically, if you're running a Bitcoin node, there are two IP addresses of a Bitcoin node: a private IP address and a public IP address. All your devices that are connected to the same Wi-Fi router will have private addresses that they use to communicate with each other. So if you have a printer and you have a laptop and you have a Bitcoin node, all of which are connected to the same Wi-Fi router, they will have a private IP, which is only available within the network, which they use to communicate with each other. If any device that is not connected to your Wi-Fi router wants to establish connection with your devices, they will need a public IP. They will need a public IP. And to connect that public IP, that is what this does. Mini UPnP library, what this does is that it converts the private IPs of your devices into public IPs so that other devices that are not connected to your router, if they want to establish connection with your devices, they need a public IP. So your Bitcoin node will have a private IP, which your internal devices will use to communicate with it. But if an external device wants to communicate with it, it will need a public IP. That is what this library does. Mini UPnP, it converts the private IP into a public IP and shares that public IP with external devices. So if somebody else's node wants to communicate with your node, if you're sitting in India and somebody's sitting in USA and their node wants to communicate with your node as an inbound peer, they need your public IP address. So this mini UPnP library, what this does is that it converts your private IP into your public IP and allows external devices to connect with you, and it is switched off by default. So if you spin up a Bitcoin node from scratch, you will have no inbound peers, and no inbound peers will be allowed to connect with you. You will only get established outbound peers. If any of you have noticed it, if any of you run your own node on the mainnet and you've noticed it, notice if you're running Bitcoin Core or any of its forks that follow the same policy rules, you will not you have zero inbound peers. You will only have outbound peers. You will have to manually enable uh, uh, like port forwarding to allow external nodes to establish connection with you, and that is where this mini UPnP dependency comes into. This had a few bugs and this had a few security issues which we discovered previously, due to which this dependency has been removed and it's been replaced by another protocol which is known as port control protocol. Okay, so now PCP instead of mini UPnP, we use PCP that converts your private IP address into your public IP address, which allows external nodes to establish connections as inbound peers with your Bitcoin core node. So that is what this PRR talks about. It gets rid of mini UPnP because it had some security issues, and now we have this PCP that is used for IP address conversion, so that external nodes can establish connection with you as an inbound peer. Right. That is all I had to share with you guys. It's 9:12 already. That's it from my end. If there are any questions, any observations, anything that you all would like to share, please feel free to do that. And if not, then we can call it a day. All right, then it seems no questions. Okay, all right, guys. So for those of you who don't have any questions or don't have anything to share, please feel free to sign off. Hope to see you guys there. Thank you. Good night.